Hi everyone, we're going to cover the topic of L'Hopital's rule. So L'Hopital is a person who came up with this rule, and I think you're going to love it. There actually happens to be a French accent on the O, and it is pronounced L'Hopital, L'Hopital. Although I know some teachers kind of joke around and call it the hospital's rule. All right, here's when we can use it. If you have a limit as x approaches some number, a, and that number can be 0, it can be infinity, negative infinity, it can be a number 7. It does not matter what this value is. Of some function that's being divided, so let's say there's a function on top, we'll call it f of x, and the function in the denominator g of x. If, when you take a and you plug it into the numerator, you get a 0, and then you take a and you plug it into the denominator and you get a 0, then you can use L'Hopital's rule, and I'll tell you what that is in a second. Or if you take a and you plug it into your numerator and you get an infinity or a negative infinity, and same thing here, you plug it into the denominator and you get an infinity or a negative infinity, you can use L'Hopital's rule. Well, what is L'Hopital's rule? L'Hopital's rule says that if this happens, you can just take the derivative of the numerator and then the derivative of the denominator, and then take that a and plug it into both, and then you'll get your answer. Again, if you get a 0 over 0, or infinity over infinity, or a negative infinity over infinity, then you can just take the derivative of the numerator and denominator and then plug in the a. So let's try this. The first step to using L'Hopital's rule is really to show that it should be used. So first of all, what happens when I plug in a 0 here and a 0 here? Well, when I do that, I get sine of 0 over 0. Well, what's sine of 0? That is 0 over 0. So this is definitely a L'Hopital's rule problem because you're getting 0 over 0. So here's what we do. We take the derivative of this, and this is going to be, and I like to put a LH on top for equals with using L'Hopital's rule. The limit as x approaches 0. What's the derivative of sine x? Well, Santa Claus is good, so positive cosine x. And what's the derivative of an x? Well, that's just 1. Okay, now we can go ahead and we can plug in 0. So what is cosine of 0? And then there's nothing to plug 0 into down here. It's just going to be a 1. Well, what's cosine of 0? It's 1. And then we'll carry the over 1 equals an answer of 1. And you should have this one memorized anyway, but sine x over x can be used to do L'Hopital's rule. All right, on this one here, we take 1 and we plug 1 in, 1 in, 1 in. That's going to give me 5 minus 4 minus 1. And then down here I get 10 minus 1 minus 9. Well, that's going to give me 0 over 0. So this one is most definitely a L'Hopital's rule problem as well. So I'm going to put equals with an LH for L'Hopital's rule. The limit as t approaches 1. And now I just take the derivative. So that gives me a 20t cubed minus 8t all over a negative 1 minus 27t squared. All right, now I'm going to just take that 1 and plug it in for t everywhere I see a t. And let me get that answer for you. Well, the numerator just becomes a 20 minus 8, which is 12, and the denominator is minus 1 minus 27. So this gives me a 12 over negative 28. I can divide both of those by what? 4. So dividing this one by 4, I get 3. Dividing this one by 4, and I get 7. And don't forget my negative. And there's my answer. All right, how about this one? Well, when we plug in, we're going to get an infinity, because e to the infinity is going to give me a huge number. And then infinity squared is also going to give me infinity. So this is a perfect setup for a L'Hopital's rule problem. All right, let's take the derivative, and I get the limit as x approaches infinity of e to the x over 2x. Now, folks, listen very carefully right now. When we plug in infinity, again, we get infinity over infinity. I should have written this, kind of looks like 2 to the x. So in a situation where you do L'Hopital's rule, meaning you take the derivative of the numerator and the denominator, it is possible that you will get infinity over infinity again, or possibly 0 over 0 again. In that case, apply L'Hopital's rule again. You're going to keep doing this, and you can do it as many times as you want until when you plug in, you no longer have a 0 over 0 or an infinity over infinity. So I'm going to go ahead and do LH again. This is going to be the limit as x approaches infinity. What is the derivative of e to the x? It's still e to the x. And what's the derivative of the denominator, 2x? Well, that's just 2. Okay, now we're at the point where we don't get infinity over infinity when we plug in. Instead, what we get is e to the infinity over 2. Well, that's going to be infinity divided by 2, which is still infinity. And I know it's a weird concept to think that infinity divided by 2 is still infinity, but infinity is a concept and not a number. You're not even making it smaller. It's already an infinite value. Even dividing by 2 makes it still infinite. All right. Last couple here. If you were to go ahead and plug 2 into number 1, you would see you get 0 over 0. So let's go ahead and let's apply L'Hopital's rule. This is going to give us the limit as x approaches 2 of 3x squared all over 4x minus 1. It does look like we can plug in now, so I'm going to do that. That's going to give me 3 times 2 squared is going to give me 12. And then I'm going to get 7 down here. So 12 sevenths. All right, same thing here in the denominator. You can see that when we plug in 2, we get 0 over 0. So I'm going to apply L'Hopital's rule. This is going to give me a limit as x approaches 2 of 3x squared all over 1. Plug right into that, and I get an answer of 12. Right, take that 2, plug in there. So I hope you like L'Hopital's rule. It happens to be one of my favorites, and I'm assuming it will become one of yours. Have a nice day.